All right, guys. Yep, it appears to be right. If this was my A, and this is my L now, lower triangular. The L will have ones on the diagonal because it's an elimination product of elimination matrices. And over here, this is U. There's nothing non-zero below the diagonal. Now these won't have ones on the diagonal usually, but it's always going to have these zeros. Well, this is right? Yeah. So this decomposition is unique, in fact, and is useful. So let's see how we can use it, and then we'll do another one for practice. So A equals LU is useful. So let's write these down. A equals LU is unique. By this I mean L and U are unique. L is lower triangular with ones on diagonal, and U is upper triangular. This decomposition is unique. Okay, so I could, if I restrict L to have ones on the diagonal and be lower triangular and U to be upper triangular, then there's a unique decomposition like this. Okay, we'll do another example. And then we should see how to use it to solve a system too. So let me give you one to do. Let's do a practice, a small one, say, and I'm picking this up without thinking about the numbers. So suppose we have A equals, let's just take something, 1, 3, 3, 5, and find L, LT with ones on diagonal, and U, UT, so A equals LU. Okay? All right, let's do it just as we just did it. We're gonna use elimination matrices first, right? So I need minus 3 times this plus this to get rid of this 3 down here. So we say E1. I keep the first row, so 1, 0, and then I take minus 3 times the first row plus the second row. All right, so what's E1 inverse? It undoes this. So it's 1, 0, and 3, 1. Okay? So this is L, in fact, because this only has one step. So let's first write, just as if we weren't able to see this all at once, E1A, because usually you're not, is just 1, 3. And then what's the bottom row? Right, 0, minus 4, right? I have minus 3 times the top row plus the bottom. Okay, right. All right, so that's equal to U. And I see that this inverse of E1 is L. If I multiply this by E1 inverse on both sides, I get E1 inverse E1A equals A equals E1 inverse U. But E1 inverse is just L. Okay, so we have, if I write it out, 1, 3, 3, 5 is equal to 1, 0, 3, 1, 1, 3, 0, minus 4. A equals LU. Should be right? 1, this row times the first, 1, 3, 1, 3, 3, and 9, minus 4. Okay. All right. Well, what now? So I think now I want to see maybe do another one like a 3 by 3 one. So for example, well, actually, let's go back and use the example we had. We had 1, 0, 4. This goes back to the last lecture, minus 1, 3. Right, this was equal to, I don't remember, 604, right? Yep. All right, this was A. And we found an LU decomposition for A. So I'll write it again here. So we found that A was equal to 1, 0, 0, 2, 1, 0, okay, so this is A. All right, this is a 0. Now, this is L, U. We did this. Okay, well, here's what we could do. I can let this product, what dimension is this product going to be? It's going to be a vector, right? This is going to be a 3 by 1 vector. So let me name that vector something. Okay, so we have L U X equals B, right? So let's call it W equal UX. So this will just be W1, W2, W3. Okay, then I can write this LW equals B. Okay, but L is already in lower triangular form, so I can do not a back substitution, but a forward substitution. So this says 1, 0, 0, 2, 1, 0, equals 6, 0, 4. So what is W1? It's immediate, right? W1 is 6. What's W2? Well, if I multiply this, I get 2W1 plus W2 is 0. So W2 must be minus 12, right? 2W1 plus W2 is 0. And what's W3 then? Well, I have W1, that's 6, plus 12, that's 18, plus W3 is 4. So this must be minus 14. Okay, so this was quick, right? Sorry that wasn't in the screen, so I just want to go through this again. I'm just looking at these one equation at a time now. And, you know, yeah, I mean, maybe you don't like doing it in your head, that's okay. But you got to admit, it's much faster. You can feel it already than to do the Gaussian elimination. It's just substitution. All right, so I found my W's. So now I got to go find my X's. I got to find my original equation, my original variables, right? So we have now, I have UX equals W. So U was 1, 0, 4, 0, minus 1, minus 5, 0, 0, minus 2, X, Y, Z equals W. So that's 6 minus 12 minus 14. Okay, well now this is official true back substitution, and we get this equation, Z, it's immediate. Z is 7. Okay, I get minus 35. I add it here, I get plus 23, so Y is minus 23. And now I put these both in, so I get plus 28. I subtract it, so I get X is minus 22. So the point is, do two substitutions, is many fewer operations than Gaussian elimination and one substitution. And in fact, it's many, many fewer than just the Gaussian elimination alone once n is bigger than 4 or 5. So for n is 100, it's ridiculously faster. So it's definitely worth doing and something you should understand. Okay. Well, let's stop here and we'll continue more next time. We'll see you in class on Monday. We really need our class on Monday. So we'll go through this more, but it's good if you watch these now. I don't know why I'm saying this at the end. I think I'll just cut this off anyway and end it right here. All right.